Okay, so now we move to the final section of this lesson, problems involving elastic energy. Okay, so we can solve problems involving elastic energy using the principle of conservation of mechanical energy and the work energy principle. So these are principles that you learn in M2, right? Okay, so when no external forces other than gravity act on a particle, then the sum of its kinetic energy, gravitational potential energy, and elastic potential energy remains constant. So this is actually what? This is the principle of conservation of energy. Okay, so principle of conservation of mechanical energy. This is the law of conservation of energy. However, so that is if there are no external forces. If there are no external forces, we say energy is conserved. But if there is a resistive force, if there is some kind of a resistive force, what happens? If there is an external force, then we apply the what principle? Do you remember the principle you learned in M2? We apply the work energy principle. The work energy principle is where the work done by the resistive force is equal to the change in energy. Okay, so we will do some questions with these and let's see how these sums are done. Okay, so we'll move to exercise 2D question number 1. An elastic string of natural length L and modulus of elasticity mg has one end fixed to a point A on a smooth horizontal table. Do you see that? This is a smooth horizontal table. Okay, so question number 1, let's draw the diagram. So you have a smooth horizontal table. Okay, the other end is attached to a particle P of mass M. A particle is held at a point on the table with AP 3/12. So when they say AP is 3/12, what do you understand? Natural length itself is L, isn't it? So AP is 3/12 means it is 3/2 means 1.5. 1.5 L means we have stretched it and we are releasing. So find the speed of the particle when the string reaches its natural length. Okay, first let's mark all the information. What do we have here? So first thing is let's mark the string. So this is the string and this is the particle. Okay, so okay, natural length is L. Let's mark that. Natural length is L. Okay, and so they say here AP, right? The fixed point is A. Here this fixed point is A. The other point is where the particle is. So AP is 3/12 means the extension is L. So 1L plus another half L, right? Do you agree with me? Extension is half L. Okay. And then they're asking you, okay, so you're releasing the particle from here. Okay. So they're asking you find the speed of the particle when the string reaches its natural length. Okay, so you release the particle at this point and they want you to find the speed with which this object reaches its natural length. You do realize the moment you release it, it's going to accelerate, right? There was we learned how to calculate that initial acceleration in the previous section. So this is going to accelerate and come towards the center. And when it comes towards the natural length, they are asking you what? To find the speed at this point. Right? So you come to this point. When you come to this point, actually, what is the velocity? What is the speed? Okay, so we are going to mainly do this, children, by using the principles of energy. Now, when you look at this particular system, do we have any external force or any resistive force? They say this is a smooth horizontal table. Do you notice the word? So there are no resistive forces, which means energy is conserved. So we can go mainly with the rule of conservation of energy. By the law of conservation of energy. So what do you have here? At the point P. Point P is where we release it. So you release it from rest, right? If you are releasing it from rest, what energy do you have at point P? Do you have kinetic energy? No, you're releasing it from rest, zero velocity. Here you don't have gravitational potential energy because we don't have a height difference. But what energy do we have when you stretch an elastic string? You have the elastic potential energy, isn't it? You have the elastic potential energy at this point. So when it comes to the natural length, okay, from point B, it comes to its natural length. When you come to the natural length, what energy do you have over here? They say they have a velocity here. So you have kinetic energy. Do you have elastic potential energy at this point? No, why? The extension is 0. You don't have any x value. You are back at the natural length. So there will be no elastic potential energy. So you could write it like this. Now your elastic potential energy you have over here when you're coming towards the natural length, are you gaining in elastic potential energy or are you losing it? You're losing it, right? So the elastic potential energy that you are losing will be equal to what? Over here, you are gaining in what? When you come to this point, you are gaining in kinetic energy. So the elastic potential energy that you are losing is equal to the kinetic energy gain. Okay, so elastic potential energy is lambda x square over 2L. Kinetic energy is half mv square. Shall we input the values? Lambda is the modulus of elasticity is mg, right? X is half L. The extension is half L. So half L u squared divided by 2L. 2 times natural length is L equals half mv square. So m cancels out. M cancels out. You could also make v square the subject by taking 2 to the other side. Let me take it in the next step. So what do I get here? Half L square. This becomes 1 over 4L square times the G. Divide by 2L. Do you agree with me? This is equal to half V square. Okay, so I can cancel out L. And 1 over 4 and the 2 here will multiply to give you 1 over 8 GL, right? 1 over 8 GL equal half V square. Do you see my rearrangement? I brought the 4 down here to the denominator with the 2. And you have GL here. So the 2 comes to the other side as a multiplication. 2GL over 8. So you get here V square equals 1 over 4GL. Agreed? And then you get the velocity by square rooting. Root of 1 over 4GL. I think you can see the 1 over 4 can come out as half. So half times root GL is equal to the velocity. Okay, so this is the velocity at the when the string reaches the natural length.